Hi everyone, in this video we are going to talk about the limiting points of a system of coaxial circles. The definition says that limiting points are the centers of the point circles belonging to a family of coaxial circles. That means if we take a family of coaxial circles, the point circles belonging to that family would be called the limiting points of that system of coaxial circles. Let's suppose we have a system of coaxial circles like this, and the limiting points will be the point circles. So what I'm going to do, I'm going to draw 2 points inside the smallest circle here, and those 2 points will be the point circles belonging to this family of coaxial circles. Here is one of the point circles, the red dot on the right hand side, and here is the other one. I have a green dot on the left hand side. So if you assume that the green dot and the red dot are nothing but point circles belonging to this family of coaxial circles, then these 2 dots or these 2 points will be called the limiting points. The main property of limiting points would be that their radius would be 0, and of course they belong to a family of coaxial circles. Now if we have to find the limiting points of a system of coaxial circles, then that would mean that we have to find the coordinates of the centers of the point circles belonging to this family of coaxial circles. Now we are going to take a few cases. Let's take a look at the first one. In the first case, suppose the equations of 2 circles are given from a family of coaxial circles and we have to find the limiting points. That means we have to find the coordinates of the centers of the point circles belonging to this family. Let's suppose the given equation of the first circle is like this, and let's suppose the given equation of the second circle is like this. Since these 2 circles belong to the same family of coaxial circles, then we can easily come up with the general equation of this family of coaxial circles. And the general equation of the family of coaxial circles can be written like this. In the previous video, I have explained this concept. Feel free to watch that video. I have shared the link in the description also. Now if we plug in the values of S sub 1 and S sub 2, this general equation going to look like this. And then we are going to simplify a little bit. If we reorganize the terms, we can write it like this. All I have done is I have removed the parenthesis and then I have reorganized the terms. I have kept the x squared terms together, y squared terms together, then the x terms together, the y terms together, and the constant terms together. And then to make the coefficient of the x squared term and the y squared term as 1, I am going to divide both sides of this equation by 1 plus k. Then our equation would look like this. Now if this is the general equation of the family of coaxial circles, then the center of any circle belonging to this family can be written like this. The x coordinate of the center would be like this, and the y coordinate of the center will be like this. So when the equations of 2 circles are provided, we can come up with the coordinates of the center of any circle belonging to this family of coaxial circles. And then from here, if you think about it, if this is the general form of the center of any circles, then of course this will also represent the centers of the point circles belonging to that family. That means if we can somehow find out the suitable values of k, then using this particular formula, we can come up with the coordinates of the centers of those point circles belonging to this family. That means we can find out the limiting points. Now how are we going to find the suitable values of k? Well, we are going to apply another condition for the limiting points. The condition is that their radii will be 0. Now from this general equation, what will be the radius of any circle belonging to this family? The radius will be like this. All I have done is I have noted it as square root of g squared plus f squared minus c. Now if this is the radius of any circle belonging to this family, then for limiting points we know that this radius will be 0. So we can say that if this radius is equal to 0, then the values of k that we are going to find out can be used to determine the coordinates of the limiting points. And if you think about it, you can clearly see that if we take a square on both sides, ultimately we will end up with the quadratic equation involving k, and from there we can find 2 values of k. And then we can use those 2 values of k to determine the coordinates of the limiting points. I hope the steps are clear. Next, we are going to take another situation. In the second case, we have been provided with the equation of one circle belonging to the family, and also we have been provided with the equation of the radical axis for that family of coaxial circles. And from here, we have to find out the limiting points, I mean the coordinates of the point circles belonging to that family of coaxial circles. Let's suppose the given equation of the circle is like this, and let's suppose the given equation of the radical axis is like this. And using these 2 equations, we can easily write down the general equation of the family of coaxial circles. It can be written like this. In the next step, I'm going to plug in the values of S and L. So our equation will look like this. And then I'm going to remove the parentheses and reorganize the terms a little bit. Our equation would look like this. And then I'm going to do just one little trick in the x term and the y term. I multiplied by 2 and divided by 2. So our equation could look like this. And the reason I am doing this is I am trying to express this equation in the form of the general equation of a circle, like x squared plus y squared plus 2gx plus 2fy plus c equals 0, so that we can easily see what is the x coordinate of the center and what is the y coordinate. So from this equation, we can say that the center of any circle belonging to this family would look like this. Now, if we can somehow find out two suitable values of k, then using those values of k, we can calculate the limiting points. Now, to find the values of k, again, we are going to use the same technique. We are going to use the formula for the radius and we are going to equate that to 0. And from this equation, we are going to get two values of k, because this will become a quadratic equation in k. And then by solving this equation, we are going to find two values of k. And then using those two values of k in the formula for the location of the center, we can come up with the coordinates of the limiting points. And that's what I have noted here. So by solving for k, we will find two values of k, and then using each value of k, we can find each of the two limiting points. I hope the steps are clear. Next, we are going to take another situation. In the third case, let's suppose that the equation of the family of coaxial circles has been provided. That means the general equation of the family of coaxial circles has been provided, and from that equation, we have to somehow find out the limiting points. That is the coordinates of the point circles belonging to that family. Let's suppose the provided equation for the family of coaxial circles is like this: x squared plus y squared plus 2gx plus c equals 0. Here g is a parameter. Using various values of g, we get equations of various circles belonging to that family. From this equation, we can clearly see that the coordinates of the center of any circle belonging to this family would look like this. And this will also represent the limiting points belonging to this family. Of course, the criteria is that for limiting points, the radius has to be 0. Now, in this case, what is the radius? Well, the radius will be like this. It would be square root of g squared plus f squared minus c. In this case, f is 0, of course, there is no y term. And from here, we can say g squared minus c equals 0 if we take a square on both sides. And from there, we can say g squared equals c. And now we have two values of g. Those are positive and negative square root of c. So then, the coordinates of the centers of any circle belonging to this family of coaxial circles would be like this. I have noted it in white color with a light green box. It would be positive square root of c, 0 and negative square root of c, 0. And next, we are going to see what is the necessary condition for a family of coaxial circles to have real limiting points. There may be some families of coaxial circles that may not have limiting points. Now, what is the criteria? Well, if you see, the x coordinate of the center of any circle belonging to this family is square root of c. So that square root of c, the value of c will dictate whether the limiting points exist or not. When c is positive, the limiting points of course going to be real and distinct, because we are going to have a real value for the square root of c. So that means we are going to have two unique sets of coordinates for the two limiting points. When c is equal to 0, the limiting points of course will coincide with the origin. That means the coordinates of the centers of any circle belonging to this family would become 0, 0. That means the centers of any circle belonging to this family of coaxial circles will become 0, 0. And the third scenario is when c is negative, the limiting points are imaginary. Why? Because if c is negative, square root of c will become an imaginary number. That means there will be no real limiting points for this system of coaxial circles when c is negative. So just by looking at the value of c from the given equation of the family of coaxial circles, we can easily say whether this system has real limiting points or a coinciding limiting point or no limiting points. I hope things are clear up to this point. Next, we are going to look at another scenario. In the fourth scenario, we have been provided with the equations of one circle and one limiting point belonging to a family of coaxial circles. And from there, we have to find out the other limiting point. Let's suppose the given equation of the circle belonging to a family of coaxial circles is like this. And also let's suppose the coordinates of the given limiting point are like this: x sub 1, y sub 1. Since we have been provided with one limiting point, we can easily come up with the equation of a circle using the coordinates of the limiting point, and that equation can be written like this: x minus x sub 1 whole squared plus y minus y sub 1 whole squared is equal to 0 squared. Now this is the most important part, because I am trying to come up with the equation of a circle whose radius is 0, then the equation should be written like this, because I am dealing with the coordinates of the point circle belonging to this family. And if we expand this equation, it can be written like this. And then if we reorganize the terms a little bit, it can be written like this. And let's call it S sub 2. Let's call the left hand side of this equation as S sub 2. So now we have equations of two circles that belong to this family of coaxial circles. One equation was already given, and using the coordinates of the limiting point, we have been able to come up with another equation. So now using these two equations, we should be able to write down the general equation of the family of coaxial circles, and it can be written like this. And then I'm going to plug in the values of S sub 1 and S sub 2 in this equation. Then the equation would look like this, and in the next step I am going to remove the parentheses and reorganize the terms. So our equation would look like this. And then finally I am going to divide both sides of this equation by 1 plus k, so that the coefficients of the x squared term and the y squared term will become 1. Our equation would look like this. And from here we can easily note down the coordinates of the center of any circle belonging to this family. And the coordinates of the center can be written in the general form like this. Now for it to represent a limiting point, the radius has to be 0. So we are going to use the same technique. We are going to note down the radius and we are going to equate that to 0. And then from there we will be able to find two values of k, and then using each of the values we should be able to come up with the limiting points. Now using the two values of k, of course we will come up with the two limiting points, but one of them has been provided and we should be able to identify that. And then of course the other one will be the other limiting point that we were supposed to derive. I hope the steps are clear. Next, we are going to consider another situation. In the fifth scenario, let's suppose we have to find the equation of the family of coaxial circles when the limiting points have been provided. That means we have been provided with two sets of coordinates which represent the limiting points for a family of coaxial circles, and from those two coordinates we have to somehow come up with the general equation of the family of coaxial circles. Let's suppose the given coordinates are like this: x sub 1, y sub 1 and x sub 2, y sub 2. Now using the coordinates of the first limiting point, we can come up with the equation of one circle. It will look like this because it represents a limiting point, that means radius will be 0. So we can write down the equation of one circle like this, and if we expand it we can write it like this. And then I'm going to call the left hand side of this equation as s sub 1. Next we are going to come up with a similar equation using the coordinates of the second limiting point. The equation would look like this, and then we are going to do the same thing. We have expanded the equation, and here I am going to call the left hand side of this equation as s sub 2. So now we have two equations of circles belonging to this same family of coaxial circles, and using these two equations we should be able to come up with the general equation of the family of circles. We know that the general equation of the family of coaxial circles can be written like this when we are provided with two equations of circles. In this case we were provided with the coordinates of the limiting points, not the equations of the circles, but using the coordinates of the limiting points we have been able to come up with two equations of circles belonging to that family, and then using those two equations we can write down the general equation of the family of coaxial circles. Next I am going to plug in the values of s sub 1 and s sub 2. Our equation would look like this, and then I am going to remove the parentheses and reorganize the terms. Our equation would look like this, and then I am going to divide both sides of this equation by 1 plus k, so that the coefficients of the x squared term and the y squared term become 1, and our equation could look like this. So this is the general equation of the family of coaxial circles when we are provided with the two limiting points belonging to that family. So this is how we can come up with the general equation of the family of coaxial circles when we are provided with the two limiting points belonging to that family. I hope things are clear up to this point. And finally, we are going to talk about one special property of limiting points. The special property says that every circle that passes through the limiting points of a family of coaxial circles orthogonally cuts every circle of that coaxial family. Now first let's try to visualize this property. Let's suppose we have a family of coaxial circles like this with two distinct limiting points, the red dot and the green dot. And then any circle that passes through these two limiting points, they will cut each circle in this family orthogonally. So now let's see how those circles going to look like. Let's suppose we have a circle like this that passes through the two limiting points. Then this green dotted circle would cut orthogonally each of the white circles. Now can we draw another circle? Sure, we could have another circle like this, but it also passes through the same two limiting points, and this larger green dotted circle will also cut each white circle orthogonally. And similarly, I can draw a bunch more circles. Here is another circle that also cuts each white circle orthogonally. And similarly, we can draw many circles like these that would pass through the two given limiting points, and each of these green dotted circles would cut each circle in the original family orthogonally. That means each of the green dotted circles would cut each of the white circles orthogonally. Now all the circles in this set, the white circles as well as the green dotted circles together, they are called the Apollonian circles. Now there is also a proof that each of the green dotted circles would cut each of the white circles orthogonally, and we are going to see that proof in this last part of the video. Let's suppose the general equation of the coaxial family is like this, where k is a parameter, and I am going to number this equation as equation number 1. And we have seen in this video that the two distinct limiting points can be written like this. One would be positive square root of c comma 0, and the other one will be negative square root of c comma 0. And then I'm going to now talk about the equation of the green dotted circles that we just saw in the diagram. So if we assume that the equation of the green dotted circles is like this, here the constant term is being called lowercase a instead of c, because I have already used the lowercase c in the previous equation. So in this equation I'm using lowercase a as the constant term, and I'm going to number this equation as equation number 2. And since this equation represents each of those green dotted circles that pass through the limiting points of the original family, then this equation should be satisfied by the coordinates of each of the limiting points. Now let's plug in the x coordinate and the y coordinate in this equation. So the equation would look like this, and if we simplify a little bit, it would look like this, and I'm going to call it equation number 3. Similarly, the coordinates of the other limiting points should also satisfy this equation, and let's plug in the coordinates in this equation. So it will look like this, and then we are going to simplify a little bit, and it is going to look like this, and I'm going to call it equation number 4. Next, I'm going to subtract equation number 4 from equation number 3. We are going to get something like this, and because we have assumed that there are two distinct limiting points for the given family of the coaxial circles, definitely c is not 0 or negative, c has to be positive. So in this case, because c is not 0, we can divide both sides by the square root of c, then we are going to end up with g equals 0. And then from equation number 3, by plugging the value of g, we can get a equals negative c. So now, what would be the equation of all circles passing through p sub 1 and p sub 2? Well, we can write it like this. All I have done is I have taken that yellow equation, I mean equation number 2, and then I have plugged in the values of g and a. So the equation would look like this, and then we are going to simplify a little bit. The simplified form will look like this: x squared plus y squared plus 2fy minus c equals 0. And in this case, f is a parameter because it represents all the circles passing through the two limiting points. So f better be a parameter. And also we have been provided with the equation of the coaxial family, and that equation was like this, and let's call them equation number 5 and 6. Now what is the condition of orthogonality? Well, condition of orthogonality is like this: when the equations of the circles are like x squared plus y squared plus 2g sub 1x plus 2f sub 1y plus c sub 1 equals 0, and the second one is x squared plus y squared plus 2g sub 2x plus 2f sub 2y plus c sub 2 equals 0, then the condition of orthogonality between those two circles would be like this. So in this case, we have two equations, and let's see if 2 times the product of g sub 1 and g sub 2 plus 2 times the product of f sub 1 and f sub 2 is equal to c sub 1 plus c sub 2. So first we are going to do the left hand side. The left hand side can be written like this. If you carefully look at equation number 5 and 6, in equation number 5 the value of g is 0, and in the second equation the value of g is k. And similarly, if you look at the equation number 5 and 6 again, the value of f in equation number 5 is actually f, and the value of f in equation number 6 is actually 0 because you don't have the y term in the equation number 6. So then 2g sub 1 g sub 2 plus 2f sub 1 f sub 2 can be written like this for equation number 5 and 6. And if you carefully notice that this actually equates to 0. Now if we can also prove that the right hand side is also equal to 0, then the condition of orthogonality will be satisfied, then our proof will be completed. So the only remaining work here is we have to somehow prove that c sub 1 plus c sub 2 is equal to 0. Now if you think about the constant term in equation number 5, that is a negative c, and if you think about the constant term in equation number 6, that is a positive c, so their sum will obviously be equal to 0. That means we also have been able to prove that the right hand side of the condition of orthogonality is also becoming 0 and the left hand side already became 0. That means both the left hand side and the right hand side, they are equal. That means the condition of orthogonality is satisfied for equation number 5 and 6. That means any circles represented by equation number 5 will cut every circle represented by equation number 6 orthogonally. I hope everything made sense. Thank you for watching. See you in the next video.